In a line carrying ash, coal, sand, or slurry at speed, the grit hits the pipe wall thousands of times a second, and at every bend it strikes hardest, cutting through steel in a matter of weeks. A silicon carbide wear-resistant pipe takes that punishment where steel gives up. A ceramic bore hard enough to shrug off the abrasive stream and keep the line running long after a metal pipe would have worn through. Silicon carbide sits near Mohs 9.5, close to diamond and far above hardened steel or wear-resistant cast iron. Because the abrasive particles are softer than the wall they strike, they slide and bounce off instead of cutting in, which is why the pipe lasts many times longer than a metal one in the same duty. The bore is dense and smooth, so the flowing material meets low friction and slides through cleanly rather than dragging. And because silicon carbide is chemically inert, the same pipe resists the acids and alkalis that often ride along with an abrasive slurry, wear and corrosion handled by one wall. It holds its strength and its shape in hot, pressurized lines, carrying flow up toward 450 degrees and around a megapascal without softening or creeping. Hard, smooth, inert, and heat-stable, the wall does several jobs a metal pipe cannot do at once. Erosion is not one process but two, and the difference is the angle the particle strikes at. Hit a ductile metal at a shallow, grazing angle and the grit cuts it like a tiny blade. Hit it straight on and it batters the surface instead. A metal pipe wears fastest at a shallow angle, which is exactly the angle particles take along a pipe wall and around the outside of an elbow. Silicon carbide changes the rule. Because it is so hard, the shallow grazing particles cannot cut into it the way they slice a metal, so its wear stays low at the very angle that destroys steel fastest. That is the physics behind the numbers. A silicon carbide pipe lasts on the order of 10 times longer than alloy steel, and several times longer than an alumina one, in the same grazing flow duty. It matters most at the bends. The outside radius of an elbow takes the hardest, most direct hits, and that is where a metal pipe fails first. So the ceramic is placed exactly there, evening out the wear life so the whole fitting reaches the end of its service at once rather than failing at a single worn-through spot. Sizing starts from the flow the line has to carry. Bores commonly run from around 50 mm up past 400, with the ceramic wall thickness chosen for the abrasion. Anywhere from about 6 mm for light duty to 45 for the harshest, and the elbow radius set to keep the particle angles gentle. From there the shape follows the pipeline. Straight lengths, elbows at any angle, reducers, and tees are each lined to suit the run, and on a bend the wall is often made thicker on the outer radius where the wear is worst. So material is spent where the grit lands, not wasted where it does not. Ends come flanged or plain to drop into the existing line. In a pneumatic conveying line, the kind that moves fly ash or pulverized coal through a power plant, dry solids are blown along the pipe at speed, and every elbow is a wear point where the stream slams into the outer bend. A silicon carbide-lined run takes that impact where a bare steel elbow would thin and burst, so the line keeps conveying without the constant patching that abrasive solids force on a metal system. The smooth bore keeps the flow moving with little pressure loss, and the hardness holds the bore dimension steady so the conveying rate does not drift as the pipe ages. Cut open after a long campaign, the bore comes out barely marked where a steel elbow from the same line would have worn paper thin or blown through. The line runs longer between shutdowns because the wear point no longer sets the schedule. Resolutely, the ceramic wall holds the bore that the whole conveying line depends on, turning a weekly repair into a part that outlives the campaign.